Alright, starting today, ladies and gentlemen, we're starting Unit C. Unit C has a big picture. I like to call it electromagnetic radiation, or known as EMR. However, I divided this unit into two chapters, or part 1 and part 2 if you will. The first half we'll talk about light and any type of electromagnetic radiation using a wave model. This is very similar or what you learn in Physics 20 Unit D. When you start learning about the nature of wave and nature of sound, those kind of situation. Although we don't need it for today, as a long term, we do need two materials. One is ruler and another one is protractor. But of course, I like to focus on more ruler because we're going to learn more about lens, mirror, and light travels straight. So how can we draw line diagram that portray those light's property after the reflection, refraction, those kind of thing. And in the end, we're going to learn something like prism or some of the experiment which we're going to see in a virtual hands-on lab. So have that in your mind. Without further ado, let's start our lesson number 1. What is EMR? So here's the thing. Let's recall Unit B a bit. In Unit B, we know that any type of accelerating charged particle, and generally when I say particle, it can be proton, electron, those kind of guys. You know, the one that use left hand's rule and right hand's rule. Left hand's rule for anything negatively charged, right hand's rule for anything positively charged, like alpha particle. If you have accelerating particles, you start to create magnetic radiation. So the concept basically go along with it, electromagnetic radiation. Now, the thing is, we need to remember some of the clues some of those basic properties of wave, because radiation is basically a wave. And any source of wave actually come from any type of vibration. So source of all waves is basically come from vibration. When you say vibration, we need to remember something known as frequency, because without the frequency we cannot have a vibration. So the frequency of the wave never changes once it leaves the source. That statement over here is basically one of the main conclusion you learn from Physics 20, or should have learned in Physics 20. The frequency of the wave never changes once it's leave the source. This is one of the main reasons why, imagine I have water or pond like this, and if I drop a pebble at this area, you will notice that the wave front propagate away from the source, and this frequency, how much of this wave is occurring, doesn't change. It's very repetitive. We call it oscillation motion, and within a certain time, if it's repeat 2 times, it should repeat 2 times from here, 2 times from there, something like that. So anything involve wave, a number of cycles if you will, we call it oscillation motion, and it's repeating every single time. Although it is not a formula, you can consider frequency and formula in this way. It's not given. It's how much total number of cycle over total number of time. If this total number of time become a second, so like per second, something like that, then we call this whole thing as hertz. as a unit. Hz. So if you think about any type of radio station, 97.2 megahertz, something like that, those are the one that you can consider as a frequency. It doesn't change. That's why whenever you go to some other location, like within 100 kilometers most of the time, radio wave can be reached. So 1 hertz is basically equivalent of whatever the cycle, and this cycle can be wave as an example. Whatever how many cycle that is occur per 1 second is known as 1 hertz. Or if you want to look at the perspective of time, 1/second. So it's reciprocal. Period. This is now a formula that I am going to refer. It's given to you and you learned it before. Basically, frequency is equivalent of 1/big T. This big T is not just regular time. It is specifically how many seconds generally is what we refer. How many second, millisecond, doesn't really matter. How much time it takes for 1 cycle of repetition. So I like to highlight and put star right next to it. The time it takes for 1 cycle. And this big T time, you can consider reciprocal of my formula F over here. How much total time over total number of cycle? And units should be second. Time to time, these two can have unit of minute. And you guys learned about this before, like RPM. That's a fancy way of saying rotation per minute. So if I reciprocal that, this is a frequency example, then you will get minute automatically. It's not hertz, so have that in your mind. Hertz is per second, RPM, PM is per minute. So you need to do some unit conversion. Now let's talk about wave that you learn. There are 2 different types of wave, technically. One is transverse wave, number 2 is longitudinal. The difference between those is, for example, the source of vibration and the propagation direction is 90 degrees to each other. That is what transverse wave is. The good way of explaining that is if you have a slinky and if you go up, down, up, down, up, down, you may notice that this going up and going down, crest and trough, are the ones that actually propagate perpendicular to your motion. My motion is going up and down. However, the slinky will go up and down like a wave in ocean. And that's basically transverse wave because I am putting a force up and down. However, the wave itself going left in that situation or right if I move it like this. Longitudinal is on the other hand, if I draw a slinky, it is a little bit tough to see, but imagine I have a slinky and I'm going back and forth like this. So propagation direction and my amplitude, crest and trough, basically share the same direction. The angle is 0 degree or 180 degree. On the other hand, when it comes to this 90 degree to 270 degree, if you will, it's going up and down. So understand that when it comes to physics 30, although we are learning about these two, we will heavily emphasize this transverse wave. Basically, transverse wave, textbook definition, particles move in a direction perpendicular to the wave motion. So this perpendicular 90 degree is what I'm going to emphasize. Let's recall some of those important lessons that you learn in physics 20. This is where my origin is. And imagine if you have a wave that go all the way to the top, maximum, all the way to the bottom, minimum. In wave, this two's gap should be equal together. We call this origin to the maximum, origin to the minimum, called amplitude. Which define how much energy of the wave. Think about tsunami, those kind of natural disaster, earthquake and tsunami followed by, those are the ones that go really high up and low down because of the massive energy that is created by the earthquake. Now, we need to also remember wavelength. First of all, the symbol is called lambda, which is Greek letter. This is what we are going to use a lot in this part 1 of Unit C, because wavelength basically is one of those basic property of any type of wave. It can be sound, light, electromagnetic radiation, any of those. So let's go through one by one. Simplest way that I can explain to you is this. And this is what you may learn it in Physics 20. This is where everything starts. If I look at the pattern, and I'm going to break things down, there's going up, down, and return. And there's up, down, and return. And in this diagram, it doesn't fully show, but this one entire repeating pattern, I like to say, the length of that is what we like to call as wavelength. It's length of one entire cycle. Now, that means in this diagram, I have one wavelength, two wavelength, and actually half of the wavelength over here. Because it have only going up and return, it doesn't have down and return. So, this diagram shows 2.5 wavelength of the whole pattern. This wavelength is very tricky and unique because you don't have to always start from where I start and where I come back. You can actually compare maximum to maximum either. Like for example, I have crest to another crest. In this case, up, going to return, down, return, going up again. This segment is now become my one entire wavelength. So it really doesn't matter where you start. Even if you start from there, you're gonna end up having one wavelength, two wavelength, quarter and quarter, which makes half. So in the end, it's 2.5 in this diagram. Similar reason, I can start from this lowest part, 12, all the way to return up, return going down. That can also be my full wavelength. So it depends on your perspective. Particles that are one wavelength apart will move identically. So even if you start up and the bottom, they're in phase. And when it comes to in real life open system, due to a friction, transverse wave will lose their energy and it's gonna go slower, but the frequency will never change. So generally heat, sound energy. Think about any type of experience in ocean or beach. The wave get weaker as it reach to your beach area. On the other hand, frequency will never change. The review section doesn't stop over here. One of the ultimate formula that we are going to use is universal wave equation, which you see over here. V is equal to F lambda. Now, let's remember some of those important section of it. If the medium doesn't change, when I say medium, I'm talking about what waves go through. For example, it can be water, it can be air, it can be ice, it can be glass, etc., etc. Generally, we're talking about air most of the time, and in formula booklet, or formula sheet in Physics 30, you may see that air vacuum is written. For example, speed of light, which we're going to talk about it. The speed of the wave is constant as long as we don't change our medium. So that means, again, air to air. Nothing should be changing. On the other hand, air to water, speed will be actually decreased quite a bit. This is the reason why we're going to look at what I like to call refraction, which you learn about the phenomena in grade 7, 8, 9, somewhere over there. In any case, therefore, you can change the speed of the wave only by changing the medium. This is one of the most important diploma question of device, basically. Because in Physics 30, and especially in real life situation too, the easiest way to change of the speed of the wave is changing the medium, basically. Now, changing the frequency or amplitude has zero effect of wave speed. Changing frequency or amplitude do not have any change on the speed. In fact, changing frequency may change the energy in future. However, when I say future, it's in further lesson later, but I don't want a spoiler alert about that entirely. So right now, as long as you know that frequency amplitude change has zero effect to your wave. And the formula goes like this. V is equal to F times lambda. Frequency times lambda. Now, I'm going to explain to you mathematically. Frequency, let's say we're using hertz. Then hertz times lambda meter, right? But if you actually think about it, this concept of hertz is reverse version of period. So 1/second times by meter is what's happening. And if I combine these two together, I have meter per second in the end, which is my speeds unit. Now, this formula V, we generally use it for sound. But when we talk about EMR, this formula, I'm going to change it a little bit like this. C is equal to F lambda. And C is something that you didn't learn before. C is basically speed of light in the air that is also vacuumed. This is a maximum speed that we can have in the world of physics. Even if you go to university, there's nothing that is faster than the speed of light, or we didn't discover yet. One thing that you need to understand is frequency and wavelength generally has an inverse relationship. Like for example, source of frequency is high, wavelength goes short. Source of frequency is low, wavelength will go high. And we're going to talk about that way more in detail, possibly tomorrow. So, let's get this classic example started. For the light wave shown, determine the period of source vibration and time for the wave to travel 75 kilometers. So, let's analyze this first. Right now, I have basically my wavelength that is given, the total wavelength, 800 nanometer. Now, let's think about our pattern. Go up, down, and return. That's one wavelength. Go up, down, and return. That's another wavelength. So I have 1 plus 1, that's 2 wavelengths. So, in order to answer the period, let's figure out the wavelength first. My one wavelength is equivalent of 800 nanometer divided by 2, so 400 nanometer. That is my wavelength so far. It says this is a light of the wave. So, my speed, which is velocity in this situation, well, honestly, I'll correct it. Speed and velocity doesn't matter in that situation because direction is, well, propagate on this way, perpendicular to up and down. So let's just do the quantity. Speed is given. wavelength is given. Now, only thing I need to do is using this formula. I'm going to modify it though, because it is asking the period, big T, basically. I can just substitute instead of F, 1 over big T and lambda. So in fact, C is equal to lambda over big T. And I'm going to isolate for big T and substitute everything in. 400, 10 to the power of negative 9 meter. Don't forget that nano is my prefix, so you have to put every single thing in here. So 400, 10 to the power of negative 9 divided by 3.00, 10 to the power of 8. Let's punch these numbers in. Now I have, as you may see, about the significant digit is 3 in this case, 1.33, 10 to the power of negative 15 second is my answer for the first question. Now second question, the time for the wave to travel 75 kilometer. Now don't connect this with my universal wave equation. It's actually a very simple kinematic situation. Distance is given to you. In fact, it's 75 kilometers, so 75,000 meters. I can put it in this way. Speed, instead of V, I'm going to use C because it's speed of light. And we're talking about how much time it occurs. So in fact, this question is V is delta D over delta T. And if I isolate for delta T, it is in fact V over D, which is C over D in this case, and you just need to punch these numbers in. And my delta T, once I put everything, I have 4,000 seconds. Oops, that is a little bit wrong. When I isolate it, remember, sorry ladies and gentlemen, I reversed the whole up and down. I just isolated wrong, so please double check to avoid those, which is easy fix for me. I'm just gonna do 1 divided by that, or just do everything again. 75,000 divided by 3, 10 to the power of 8, doesn't really matter. Now that's more like it. 2.5 10 to the power of negative 4 seconds. No wonder, because speed of light is enough of speed to travel around the earth 7.5, if I recall, in 1 second. So you can travel with 1 second, you can turn around the earth 7.5 times, which is amazing speed. So no wonder it takes about just 2.5 10 to the power of negative 4 seconds. Now, before we getting into the world of EMR, we need to learn about, this is now new stuff, Maxwell's law. Although we don't talk about Maxwell's law a lot in detail, especially when it comes to calculation perspective, still, you have to know some of the mathematical relationship. There are 3 you need to understand. James Maxwell, in late 1800s, he discovered the relationship between electric field, magnetic field, and light. These 4 laws you need to remember. Number 1, the distribution of electric charge is basically related to the net electric field that is produced. So what I mean by that is, if I shoot up 1 electron, that amount will be converted into net electric field through the process, assuming that there's no energy loss and so on. Magnetic field, are also created actually through this process as continuous line. However, the electric field and magnetic field are created as 90 degree to each other. And that's something that I want to point that out in here. Magnetic field, electric field lines are perpendicular 90 degree to each other. The changing electric field basically produces magnetic field. Electric field affect magnetic field. And changing a magnetic field throughout this process also produce electric field. So these two are helping each other throughout the process, if you want to think it in that way. And this does cause induction situation, which what we learned in Faraday's law and Lenz's law in previous situation. An electric field can definitely accelerate a charge from the rest, and this will cause induction of the current, but magnetic field doesn't. It follows then that by changing magnetic field, an electric field is also created because changing magnetic field causes electric field to occur, and that's Faraday's part that we'll learn in Unit B. And that induces a current. So everything is intertwined each other, which is really tough to understand in this perspective. So I'm going to show you one of the famous diagram, in fact. Electromagnetic radiation. I'm going to use this graph to explain to you what that means. So let's say I have some kind of accelerating charge, electron, for example, proton, etc., alpha particle, whatever you want to call. Now, the thing is this. It's accelerating towards left to right, you can think of, with the speed of light. Then what happens is, electric field is generated up and down as a wave fashion. So you will know that it's going up, down, up, something like that. But because of this electric field, we can create magnetic field, and that magnetic field, unfortunately, in this situation is 90 degree to each other. Like this. And by having this magnetic field, in the end, it induces the electric field and it creates electric field. So it's constantly reoccurring and rehelping each other. One thing that you need to understand in physics study is electric field, magnetic field, and speed of the acceleration of a certain charge. They are all 90 degree to each other. Very similar as my left-hand rule, if you will. So the electric field, magnetic field, velocity are all perpendicular to each other, and this existence of EMR was verified by Hertz in 1886. Now, magnetic spectrum. Something that you have to memorize. The only course that you don't need to memorize this is basically Science 30 because their booklet provided you this chart over here. I'm gonna be honest with you. I'm not expecting you to memorize a certain value of wavelength and frequency. If there is, however, visible spectrum is a good idea to memorize. It's about 300 to 700 situation. Nanometer. Now, here's the thing. The large wavelength are on the left side of this spectrum. Depends on what spectrum you're studying. It can be other way around. Gamma ray is the lowest wavelength that you can have. Now, if the wavelength is high, that means frequency is working opposite. Frequency is very low. And if I have very small wavelength, in the end you have very large frequency. And I'm gonna show you a little bit of a correlation. If I have low frequency, that means low energy. If I have high frequency, that means high energy. These two energy section is something that you will learn in further lesson. Now, something that you need to understand. The biggest wavelength that you will get is radio wave. That is the biggest. Followed by microwave, the one that you use in the kitchen to warm up your food. The way that is warm up is this microwave basically vibrate the water particles. And the molecular level, water get excited, and that's how things are heated. Infrared is what you will see after that. And visible spectrum, and ultraviolet, X-ray, and gamma ray. UV, you may know. Some of the thing that you should know is UV beta B radiation is the one that basically kills skin cells and all, and it mutates the DNA sequences of your skin cells, so it causes cancer, skin cancer. Those are common knowledge that you should know for Bio 20 and Bio 30. Now, I'll tell you the easy way to remember this. Infrared, ultraviolet, red on the left side, violet on the other side. Because this is now color spectrum, your rainbow. Red, orange, red, orange, yellow, green, indigo, violet. There you go. Sorry, it took a long time for me because I used to remember in Korean. But red, orange, yellow, green, blue, indigo, violet. That's the order. And anything that go above that is infrared, which is your heat energy. If you play any type of game, they use infrared glass goggle. You guys understand, like, you know, the green background, glowing ones, something like that. Ultraviolet equals more powerful violet, so that's why it's called UV. And then X-ray and gamma ray. X-ray, for example, is so strong that it penetrates our skin, but it's reflected and absorbed by your bone. So that's why people use X-ray for some of our tests. And gamma ray over here. That is our lesson for today. Your to-do list is basically going through the homework question of everything, both A and B, and I want you to double check with your solution, which is at the bottom, but obviously don't merely copy it, write down your rationale. That is your today's lesson.